and then we'll get started. Rose's internet went out, so she will probably be late. Okay, cool. That's not a problem. There's a recording from second period that's already up. So if she can't make it for whatever reason, she can just watch that one. I posted that from this morning, so we're good there. So good morning, good morning. Let me lift this up a little bit. Not too much. Cool. Thank you guys for being here. Happy Thursday. If you're here right now, wonderful. If you're at home watching this, that's cool too. We are going to start trig today. And the way that I think it's going to work out is that we shouldn't need to live stream tomorrow. I think it's been a busy week, and I know we're going to live stream at least twice next week, but probably more like 3 or 4 times to get some lessons in. So I figure I'd give you a Friday as a practice day for the things that we do learn today at the start of chapter 4. There are actually 3 chapters dedicated to trig. Chapters 4, 5, and 6 in our textbook. We certainly won't get to every section. We probably will barely make it into chapter 6 at all. We'll kind of bounce around a little bit. I took a peek at this semester's college trig final to give me a clue for what they think was most important. So I'm going to kind of design at least like this week, next week, and then, into January a little bit around those ideas, and really just kind of cover the basics of what we're talking about when it comes to trig. I need a pen. I want to write some stuff down. You probably should too. I did link a Google slide that I will kind of periodically share my screen to, but it's also right on the announcement for today. You'll also notice that on the announcement for today, if you just pulled it up recently, I attached the notes that I wrote during second period, and I'll do the same for you and fourth, because it's the same stuff, but different words come out of my mouth in different orders. So I will take pictures of the board every time. Now that we're kind of fully remote, every time we do this, I will make sure that I take pictures of the board and post them to that day's announcement. So you can always go back and look at those in case maybe you just want to, be present and learn rather than write. Because I know that the moment you start writing, it's hard to keep 2 eyes on your paper and 2 ears on me at the same time. So keep that in mind as you go. Maybe you listen more and write less to start. Definitely plenty of important ththings that we're going to talk about today, though. When it comes to chapter 4, let me make sure I'm not up too high. So, we're going to bounce around a little bit, but trigonometry. Okay. What I want to try to get us, I want to get us to a point where we have a really strong basis for how to deal with trig, what it really means, what it gets us to be able to do, why it's so fascinating to me. You're gonna hear so many things that I love about this. This is, out of all of the things that aren't calculus, trig is probably my favorite because of how applicable it really is in so many things. Now, trig technically means, and you don't really have to know this, but triangle measure. Geometry measure, right? The trigo is the triangle part. But we're not even going to get to triangles necessarily today. Thinking about special right triangles and sine and cosine and all that stuff, that'll come soon. I want to first deal with kind of the beginnings of where all that started. And I know it's like triangle measure, but it's just so much more than that. It's understanding the relationship that is created between angles in triangles and the sides of those angles. And the question of that dates back just thousands and thousands of years. We find ancient, Persian and Arabic mathematicians and Indian mathematicians and the Greeks asking questions about pyramid shapes and the shadows that are cast from the sun over a monolith as the sun moves its way through the sky, and like they were asking these really philosophical and deeper types of questions based on kind of simple shapes like triangles. But what's cool about this idea with trig is that it doesn't just apply to triangles. And I think that's the thing that makes it the most interesting for me, is how many different ways we can try to attach this idea of trig to different kinds of shapes, right? Because you can draw a triangle inside a circle, or you can like draw a circle inside a triangle, or an ellipse, or a parabola, or spheres, and you get into pyramids and all sorts of this cool stuff. And like how those kinds of things make it just so much easier to understand everything else. I mean, like parabolas for satellite dishes and projectile motion, right? You throw something through the air, what path is it going to take, right? Those ellipses I was talking about, an oval, when we talk about like elliptical orbits of planets around stars, and trying to measure those distances and the tracking of the movement of stars, and where we are, relating circles to spheres, like trying to relate the second dimension to the third dimension. Because if you can go from the second to the third, then maybe we can think about going from the third dimension to the fourth, and then from the fourth to the fifth, and the fifth dimension to the sixth dimension, and on and on, like that. I don't know, like just talking, like you probably saw it last year in Algebra 2 Trig, if you took that class and you looked at sine waves, right? That when we look at trig graphically and we start making our way around, and we'll look at that, it takes these waves and what moves in those kind of pattern? Well, light particles move in waves, right? Sound moves in waves. X-rays, radio waves, microwaves. I mean, they literally named the appliance after the wave that is heating your food when you press the button on the microwave. I mean, it's just crazy. There's just so many different things that we can use trig to better understand. And to me, it's the universe, right? And for me, like trying to attach and I'm going to get a little deep here, but like the meaning of life, to me, one of them is to understand life, and not just mine, but yours, out there. But like to better understand, like to have a grasp of the universe, I just got to show this to you. This is just too cool. I got to share something with you. There's this website that I have probably spent just way too much time on, that I hope you also get lost in a little bit. And I just want to show it to you for a couple minutes. It's called The Scale of the Universe. This here is using Flash, which is a dying programming tool. I know that Google Chrome is, I think, discontinuing it at the end of this month, but it's still alive right now. So I wanted to show it to you. It might be a little bit choppy because I'm sharing my screen. Ooh. Oh, isn't that nice? Ooh, I like that. I'm going to mute it though, although it does give a nice little background to it. Okay, cool. I'll mute it. Okay, here we are. Okay. This is scale of the universe, and they're going to use meters. And this little bar along the bottom here, you got this little thing that you can click on, will allow you to change the scale of the universe and give you kind of a better sense of what these things mean. And what's cool, like you can click on all these things. The dodo bird goes extinct in the 1600s. You can click on us, and it starts to move you in and out a little bit. Oh, look, there's a basketball. And so you can click on this, and it kind of moves you in and out. I'm going to go out first, because the only way that we're able to measure these kinds of things, but also create something that looks like this, is with proportions. And trigonometry is proportions. That's all it is. So check this out, because there's some really, really cool stuff that maybe you don't really understand how big or how small some of these things are. Like there's an FM radio wavelength, okay? And we measure wavelengths. We go like from the top to the top, or from the bottom to the bottom, or the middle to the middle, or whatever it is. Look how long that is, right? Those things are just flying through the air all the time, smashing into you. You have no idea. Pretty crazy stuff. I also like that some of these things like move, like this albatross. And what is that thing? My goodness. The Japanese spider crab. My goodness, that's pretty cool. But as we get bigger and bigger and bigger, like you don't really realize how small some things are or how big some things are, right? I mean, you see a way to kind of measure things that we really either can't measure or we really just want to try to understand better. And I mean, airplane travel doesn't exist without trig. Architecture, like building the Statue of Liberty, building the International Space Station, the Titanic, the Eiffel Tower, the Gateway Arch in St. Louis. There are those pyramids that I was talking about. They couldn't do that without trig. I mean, building the Hoover Dam was such a massive undertaking. There's the Burj Khalifa, which I believe is in Dubai, which is as tall, if not taller, than Vatican City is wide. Now, yes, Vatican City is the smallest country in the world, but we're talking about a country, right? That's crazy. There's the Boeing Everett factory. I've actually been there. It's the largest building in the world. Unbelievable. Yeah, it's crazy. But what's cool is that we can understand this scale by putting them next to each other. There's an AM radio wavelength. Look at that. From the wavelength of one AM radio wave is as wide as Vatican City. That's crazy, all right? Those things are flying through the air all the time. We have no idea, okay? But like trying to be able to measure things that we otherwise wouldn't be able to measure, that's where trig comes in, right? Halley's Comet and neutron stars. I'm gonna start to go a little bit faster here. You can see down here the scale that we're working on. There's 10 to the 5th in terms of meters. So that's 1 with 5 zeros. So you're talking about 100,000 meters across at this point. I mean, we get to whole entire states. Did you know that California is bigger than Italy? There's Pluto and the 4 Galilean moons and the Earth, and we start to get into this one's cool. There's the size of Minecraft. The Minecraft world is wider than Neptune, not quite as wide as Saturn. But how do you think we can measure all this stuff when we don't have a ruler that can take us there, right? It's an understanding of proportion and trig, and oh, this one's cool. That's how, if we stacked all of us on top of each other, and this is actually from 2012, down here, the copyright, 2012. So this was only 7 billion people only, right? We're at about 7.5 billion people. So add, another 1/14 to this height, stack us all on top of each other. It's just crazy to think that we can even comprehend things that are this big, and look how much more space I have to keep going. Right, I won't spend too much time here. Hours and hours and hours, but all right, there's the length of a light day, how far light travels, particle of light, in one day at the speed of light. You get into nebula. I mean, you get the Stingray, you get Gomez's hamburger, which is a funky one. There's a light year. You've got the blinking nebula. I mean, study astronomy if you want to have a better understanding of life, right? It's just so cool. There's the pillars of creation down there at the bottom. Just really, really cool. All right, start to go faster. We're going to get bigger and bigger and bigger. I don't know how much you know about where we exist in the universe. This isn't a map of the universe. Remember, this is a scale of the universe. Everything is just kind of centered. But you start to get into these galaxies. There's ours, right? There's the Milky Way. And a couple of our neighbors, right? Andromeda, I believe, is the one that's closest to us. And there we are, right? As part of the local group of galaxies in a much larger group. Now, and look at this distance, okay? That distance across right there is this many meters, okay? A yada meter. Steal that word, it's amazing, okay? It's just so cool, all the stuff that we can do. I don't know if you know about the Great Attractor. It's basically the center of the pull of things in the kind of the family of universe, family of galaxies that we're close to. The Great War, that is kind of a good, like it's kind of sucking us towards a Great Attractor. It's just so cool. A gigaparsec. And here's the thing that really blows my mind. So there's the observable universe. Right? That's how much we can see. That's how big we think it is. Okay. And that just blows my mind. Like, and it's expanding, right? The universe is supposed to be expanding at this point, based on the best theory that we've got, which is the Big Bang. All right, let's go back in. All right, this is the part that's really cool. It might be a little bit choppy at home. I know it's even a little bit choppy for me here. Let's see how fast we can get ourselves back in. Because as cool as it is to see all these big things, what might be even cooler is to see things that are a little bit smaller. Okay. And there we go, right? There's a hummingbird. I like that the wings are moving. I just think that's cool. And you can click on all this stuff and see what's going on. But as we get smaller and smaller, we start to realize how big we are, but also how small we are in this universe, right? There's the microwave length. There's the thing that's heating up your food, about the width of a penny. Right? And we start to get into much smaller things, right? Bacteria and grains of sand and salt. Thickness of paper is actually thicker than the width of human hair. There's the smallest thing visible to the naked eye, that gray circle right there, and then we start to get even smaller, right? Infrared wavelengths, of course, we can't see those. Nuclei, red and white blood cells, chloroplasts, there's E. coli, there's red and violet light. Different wavelengths allow us to see different colors. I've actually got something cool I can show you about the color purple. I'll show that to you. Yes, violet and purple are different. There's ultraviolet. There's an HIV cell. There's hepatitis B. I mean, phospholipid bilayers and DNA, and there's a phospholipid, and there's X-rays, right? So tiny. That's why they can cut through us and allow us to see the bones without actually harming us. But carbon atoms and molecules, and we know how big these things are. That's how big, right? Hydrogen and helium. You know, all my sciencey folks out there, gamma rays, and what's really cool is we start to get a whole lot smaller, right? Uranium and electrons and chlorine and helium, and there's a proton and a neutron, and things get really small, and we get to this point at 10 to the negative 16th that we know this stuff is smaller, we just don't know how small. Okay. I don't know how much you know about the forces of the universe. We've got magnetic forces and gravity, but we also have weak forces and strong forces. There's the range of a weak force. I mean, our best understanding of the way that this stuff works is string theory, which gets us into quarks. I don't know a ton about it, and when I say I don't know a ton, I barely know anything, and I can only even just mention the words, but I can't really explain it. But let's go into hyperspace here a little bit and see if we can get down to the smallest things in the universe, the things that make up everything else. Okay, strings. Okay, quantum foam, the length of a plank, and there's a string, right? Apparently, according to string theory, the world is just vibrating. The universe is vibrating, and the things that make them vibrate are strings. And they have different lengths, they have different widths. And they have different speeds at which they vibrate. And that changes whether or not you're looking at something white, or you're looking at something black, whether I can go like that, or whether I can put my hand through it. It's all about strings. So really cool stuff. I will stop right there because I could talk about this stuff forever and nerd out on all this cool stuff. I mean, I got lost in the internet last night for sure, just thinking about trig and how much I wanted to tell you over like a 4-week period, 4 or 5 weeks that we're going to spend doing some trig. So really cool stuff. I mean, trig, music and art and architecture and space and science and obviously math and life, that's all trig. So cool stuff. All right, so there we go. I've said my piece. Now I'm going to teach you some stuff. Okay, when we talk about trig, we talk about triangle measures. The thing that's most important to start with is talking about angles, okay? How are we going to talk about them? What words are we going to use? How are we going to measure them? Where are we going to draw them? So that when I talk about an angle and you talk about an angle and she talks about an angle and they talk about an angle and we talk about angles in Japan and Australia and China and Germany and England and who cares? Or Collins, we're all talking about the same stuff. Okay, so I want to kind of give you the basics of all that. And this is kind of where the Google slide presentation for section 4.1 begins, talking about how to measure an angle. angles. Okay, so if you'd like to open that up so you have that, great. I would love to keep the camera as big as I can and not share my screen for it. But pull it up if you'd like. I'll share it in a little bit just so you can see it. But when we talk about angles, what I want you to really make sure you're okay with is that math is no longer static. It's not stuck. There's movement, there's action, there's time that passes as we work through this. And so when I draw an angle, I don't want to just kind of think about like, okay, there's the other side. I want to think about like taking this beginning side right here. Like I draw a ray, right? I give myself a starting point and it kind of just, it goes on and it can either end right there or I can make it go on forever. It doesn't matter because the angle is what I'm measuring. And I take that and I can kind of like use my elbow as a fulcrum and use it as kind of that vertex. We call it a vertex. And I'm going to move this initial side, right, where I begin, and I'm going to open it. Right? I'm going to move it through space. Okay, and we're going to do it in 2 dimensions. So I'm going to take this and I'm going to open it up, and I'm going to decide where to stop somewhere, right? And obviously what's in here is going to be that angle. But I want to really make sure that we understand that there's movement that happened to get us to that point. But I do want to eventually stop, okay? And so when I stop, I terminate. So I'm going to call this the terminal side. Okay, so you have an initial side and you have a terminal side. But drawing them kind of haphazardly in space like this with no real bearings, make it a little bit tougher to measure those angles. And so what we normally do is we put them on a set of axes somewhere. And we're going to graph things a little bit differently a little bit later on. We're not going to graph them necessarily on the Cartesian plane in like 3 or 4 weeks. But right now we will. Okay, I want to talk about graphing things in a plane that's made up of rectangles. I want to talk about rectangular graphing. Now I know like graph paper is made up of squares. Well, squares are rectangles, right? So, so when I graph it on the Cartesian plane like that, it's really nice to pick a good spot for the vertex. How about the origin? And a good spot for the initial side, okay? And what we call standard position of an angle, drawing an angle in this Cartesian plane, right, on a set of axes, right? The best spot is the positive x-axis, okay? And yeah, angles could, you know, the sides could go on forever, but usually what we'll do is we'll give them kind of an end somewhere. So think of it as if there was a point kind of at the end, so that my elbow is the vertex and the tip of my middle finger is the end of that initial side, okay? And we're going to open up some angles. Remember, honestly, like to this point, you've been taking pre-mathematics. Seriously, you really have, okay? Today and moving forward, and really once we get to calculus, that's when real math really begins, okay? Everything you've done up to this point has been preparing you for calculus. And this is gonna be a big part of it. So, when I decide to open up this angle, I can do it in one of 2 ways, right? I can take my initial side and I can open it this way, right? I can open it into the first quadrant, and we're going to use that Roman numeral 1 to denote that positive x, positive y space, okay? And we're going to go around when we do that. Because if I want to open up into the first quadrant and continue to go that way, that's the order in which we will list those quadrants: first, second, third, and fourth, right? And so maybe I open up an angle and you know, I stop, whatever, I stop like over here, okay? And sometimes I'll even draw a little arc like this with an arrow to show what direction things are moving, all right? So there's me actually moving this side through space and seeing what's going on, right? That is a positive angle. When you start in standard position and you open up into the first quadrant, those angles are going to be positive measures. Whatever system we decide to use for measuring them, degrees or radians, doesn't matter, positive angles only, okay? Now, I'm going to probably stop using the word angle, like written out like this. What I will probably do most of the time is use the symbol for angle. which looks like everything I've drawn so far. Two sides with a little arc between them. Okay, so that's the word for angle, the symbol for angle. Okay. You see that? Okay, yeah. So that's a positive angle, okay? But I could, if I wanted to, I could start at this initial side and I could drop it down, right? I could drop my movement down into the fourth quadrant. I could open up an angle. Let's say I go down this way and decide, stop wherever, and say, okay, cool. Like there's where things are going to end. That would be a negative angle. Okay, angles that open down. There's my symbol for angle. Angles that open down into the fourth quadrant. Those are all going to be negative. Okay. And I could, go as far as I wanted. I don't have to, go from the first to the second. I could go from the first to the third, the first to the fourth. I could go more than one full revolution around. I could go around and around and around and around like a tire wheel moving, right? It takes many revolutions. I can do that with as many angles as I want. And the angle measure is gonna, get bigger and bigger and bigger as I do that. Or bigger in the negative direction. That's cool too. Okay. So that's kind of our basic setup, right? Standard position, positive x-axis, positive going up, negative going down, okay? And one last little relationship that I have with kind of this graph is, well, what if I opened up multiple angles that ended at the same spot, right? What if I decided, hey, maybe I don't want my negative angle to stop right there. Maybe what I want to do is continue this trip around and end at the exact same spot. What if I had an angle, sorry, not one angle, but angles, more than one, that have the same, and we're all starting with the same initial side, so I don't have to mention that, but the same terminal side, because we're talking standard position. What if you had more than one angle that ended at the same spot? And whether it was like a positive one and a negative one, or maybe two positive ones, right? Maybe I open up an angle, I go around and around, and I make a full trip around, and then I keep going, and then I decide to stop right there, right? So I have this kind of spiral thing happening there, the way I draw my arc, but I end up at the same spot. Right? So maybe I have these three different angles, the two angles in black and the negative angle in green there, that all end up with the same terminal side. They're called co-terminal angles. Co-terminal angles, okay? That if you start, obviously in the same spot, because we're all going to start at the same spot, we're starting the initial side, but you end at the same spot too. Okay, and there's a lot of different ways to do that. You could go two positive directions, a positive and a negative, two negative directions. As long as you end at the same spot, you have those two co-terminal angles. Okay, and what you see if you're looking at the Google slide is that there's kind of a page dedicated to this, right? Talking about how to draw these angles, but also this relationship that you could start and end at the exact same spot. And what you might see, and I'm going to pull it up just for a quick sec so you can see it, is that there is some letters, some variables, some symbols that they're using that maybe you haven't seen before, okay? And I'm looking at the two graphs on the right there with the letter that kind of looks like an A and the letter that kind of looks like a B, okay? When we talk about angles, when we draw angles, and we only want to talk about angles, when we talk about the variables that we choose to use them, yeah, X and Y and Z, those are all good. Those are great, they're still variables, they're good to use. But if I want you to know for sure that what I'm talking about is an angle without question, variables for angles, if I use X, Y, or Z or whatever, if I use just a regular English letter, it could mean anything. It could be an angle measure. It could be the length of a side of a triangle. It could be whatever, right? It could be anything. It can be nothing, right? But when we talk about angles, we're going to use probably these three. Now, there's one that's the most popular. Okay, the one that you'll probably see me use over and over and over and over and over again. The only time I would ever need to use the other two is if I was in the same problem talking about two different angles, right? If I was looking at this, right? And I wanted to talk about these three different angles that all end at the same spot, okay? There's three of them. Okay, the most popular one is the Greek letter, capital letter, theta, Theta. Okay, and it looks like this. It kind of looks like an O, but then you keep going and you cross through it a little bit. Okay, so it's like an O, make a full trip around, and then you just kind of cut through the middle like that. That one's not on this particular Google slide, but you're going to see it over and over again. The two that are on there are alpha and beta. Okay, the first two letters of the Greek alphabet. Okay, alpha kind of looks like an A, which makes sense because it's the first letter. To me, I just think of like if I wanted to draw a simple looking like goldfish or something, and I would draw something like that. Right, there's the body and there's the fin. Okay, and then for beta, it looks like a B, but there's just no sharpness to it. Everything is curved and rounded. I start at the bottom, come up, and then 1, 2. And I'll draw them slightly different every single time. They're not going to be perfect. Like I made the top bit of this a little bit bigger. Maybe, maybe at the bottom part. Who cares? So it doesn't have to be perfect. You just want it to be relatively round and smooth and nice. Okay. Those are the three that we will use to make sure that when you're looking at those letters, you are guaranteed that you are looking at angles and only angles. Okay. Cool. I just want to make sure that I talked about everything that I wanted. I think I did. Good start. Okay, so that's just angles. Yay, angles, done. All right, moving on. I will take pictures of this stuff. I will make sure that I put it up for you to check out. Let's do it. Let's get to some actual stuff. Let's make sure I get it all. Okay. Am I up too high? Can you see right there? Okay. How to measure them. How are we going to actually measure out angles? Okay. There are two ways to do it. And if you saw Algebra 2 Trig last year, or even in geometry, you probably talked about this a little bit. Degrees are great. Degrees are wonderful. But their relationship to triangles and to circles and to everything else that we're going to look at doesn't really exist. It's just a measurement of an angle. It does not care at all what size shape you're in. And sometimes it's really nice to have that. I want to know what I'm looking at. I want to be able to relate not just the angle to itself, but to the radius of the circle that I'm in, or the length of the triangle that I'm drawing, or the length of the arc that it intercepts, or whatever it is. And so the best way to do that, and the one that we're going to use the most, we'll bounce back and forth a little bit, but we are definitely going to use radians the most. Okay. Now, when we talk about radians, what I want you to understand first is what a radian actually is, what 1 radian means. Okay. And so I'm going to give myself a space to work. Okay. And if I give myself, a place to start, and I draw myself, I'll make it kind of big. I'll come out to like there. If I give myself an initial side, I'll put a little end to it just to make it visible where that end is. And I open something up. Okay, let's call this the radius of some circle, because I open up some angle. But think about the path that point at the end there. This is not going to be perfect because I'm just kind of sketching it, but the path that would take as it worked its way around. Think about like sticking a nail into your tire and watching the nail move around. What path is it going to take? Of course, it's going to take a trip around the circle, right? 1 radian. I know we think of it like the length of the size of an angle, right? If you have any background in radians, you know that like we're talking about an angle measure, right? But really, it's not. What 1 radian actually means, and I'm not saying 1 pi radian, no pi, just 1 radian, okay? It's actually this length right here. It is the length of an arc, okay? And when we talk about arc length, we often use the letter S to do it, okay? 1 radian, so it's a measurement, and we're gonna call it an angle, right? So we can use theta when we talk about it, okay? 1 radian is the length of an arc, okay? Starting at the origin and opening up an angle that's got standard position, all that good stuff, that is equal to the radius from that circle, okay? That if I were to draw this whole thing around, obviously I get myself a circle, but if I'm thinking about an angle, so call that theta in there, okay? That when I deal with radians, 1 actual radian is when this length for R and that length for S are exactly the same. And that might not stand out as something miraculous, but think about that. We are able to measure, whoever did this for the very first time, and this is thousands of years ago, okay? Whoever did this for the very first time, they figured out a way to measure something that's curved, right? Go ahead, take out your ruler and measure that, right? I can't do it. Trig can, okay? And that, even the simple version of this, by talking about, arc length of a circle, allows us to do things like that, to measure things that are curved. And wait until Calc B when we start doing that stuff next year, okay? That's what's so crazy. And what's awesome about that is, okay, if that's 1 radian, well, now I can measure 2 radians. What can I do? I'll go twice as far, right? Like there's 2 radians right there, okay? And like there's 3 radians like right there, right? And there's 4 radians right there. And there's 5 radians right there. And there's 6 radians right there. And you can make your way around the circle using really nice radians. But here's the thing, right? Unfortunately, 6, and this is off a little bit, but 6 radians does not get you far enough. It doesn't get you all the way back around the circle. But what it does do is it gives us a way to deal with proportions. And man, proportions are just trig. Everything in trig is proportions. That if you give me some angle in radians, that it will always be in proportion to the length of the arc compared to the radius of the circle that you're in, okay? This has to be in radians for it to work. RAD is fine, okay? S is arc length, and R is radius, okay? And these obviously need to be in the same measurement system. Feet and feet, inches and inches, miles and miles, whatever it is, okay? And if we have this really nice relationship, then we can lean on it and we can use it. And what's really nice about that is we can reorder this however we want. I can solve for theta, yay, there it is. I could also start isolating either one of these two by just manipulating the way that this formula, it really is a formula for it to work. Like what if I multiplied both sides by R? R theta equals S, or I'm just going to reorder it, S equals R theta. I now have a formula that can measure something curved by using the length of the radius and the size of the angle that I opened up to get there, okay? And as silly as this memory tool is that I'm about to show you, this is what, I don't know why, like I was taught this in high school and I never forgot it. I don't think my teacher taught it to me. I think I just tried to figure it out. I wanted a way to remember S equals R theta. And so I broke it down letter by letter. S for S. E for equals. R for R. And theta kind of looks like an O. That was the letter O. 0, which kind of sounds like 0. Silly, I guess, but when I think of this relationship, all I have to do is remember 0, because that is 0, S equals R theta, whatever. If that helps, great. If it doesn't, that's okay. But that's a really, really nice formula that we can use. And again, so there it is, solve for theta. There it is, solve for S. I could solve for R if I wanted to by just dividing by theta. So R equals S over theta. Like, you can have your formula however you want. And now we've got this amazing relationship between, give me an angle in a circle. I can draw the arc now. I can draw this curved piece and I can measure it. As long as you know how big the circle is and how big the angle is that opened up. Or, so you give me 2 of these pieces, I can solve for the third one however you want, which is such a nice tool, right? I really, really like being able to do that, okay? But the issue that we kind of run into kind of back here for a little bit, and stop me, I know I'm talking a lot, but I want to get you out of here in like 10 minutes, is we don't get to the end, right? I don't make my way all the way back around by doing 6 radians of opening up an angle, right? An angle of 6 radians is not big enough to open it all the way around, because the circumference of a circle doesn't quite land so nicely, right? I don't know if you remember the formula for circumference. But it's 2 pi times r, okay? And what we're going to do is, as often as possible, what I want to do, I want to make that radius length, if possible, I would love to have r be 1. Because now the circumference of this circle is just 2 pi, which means it's going to take me 2 pi to get all the way around the circle. Which of course isn't 6, it's, you know, a little bit more than 6.28, all right? 3.14, okay, I gotta double that because that's pi. So it's about 6.28. So I've got a little leftover piece here, which is why when, probably for most of what we do, when we talk about radians, you're gonna see a pi in there because it allows me to divide up the circle in a nice way, right? You got this like tiny little leftover slice here, and we don't really know how big that is. Leftover slice here, leftover slice there. We wanna end at really nice spots. And using radians helps when we do that, as long as we have a pi in, okay? Because I can take, you know, one full revolution, RUV, one revolution around the circle is going to be 2 pi. So if I only wanted to go like halfway around, okay, well, that's just pi, right? That's how far that point is going to move. But it's also the way we're going to measure the angle that did that, because no matter how big that radius gets, the arc length is in proportion with that size. And so I can use radians no matter how small or how big the circle actually is, right? And of course, we're going to draw some triangles, like, yay, there's a triangle right there, or yay, there's a triangle right there. There's lots of triangles we can draw in there and start relating some sides together, okay? So that's radians, right? Big thing to know really is this relationship right here, which you can write however you want, because some of the work that I will give you for tomorrow will say, okay, here's an arc length, here's a radius, what's the angle? Or here's a radius, here's an angle measure, how big is the arc that you intercepted when you did that? Or, you know, I can give you 2 of the pieces and you can solve for the third just by picking the right version of the same formula. And we can measure things that are curved, and that just is so cool. Because so much of what we're going to do, once we get past triangles, we're going to use triangles to do it, but so much of what we do is we're measuring things that are curved and talking about waves and, you know, all that kind of cool stuff, okay? Just a couple minutes left, so I had one last thing that I wanted to mention. Of course, we talked about radians, so what's next? Degrees, right? Let me just take a picture of this with my phone, which is somewhere else, before I erase it all, so I can give it to you. This is basically what I did second period, though, so you can always look at theirs, but this one looks good. Cool. All right, real quick, let's talk degrees. And while I erase something, let me show you. There's this really, really nice math website. You can see up at the top there, mathwarehouse.com. And let me scroll up for a second. It's got algebra, geometry, trig, and calculus stuff in there. And I like this website a lot. It's pretty cool. But let's see if the GIF goes through there in the middle there. What is a radian? Yeah, so you see that it's taking that, the measure of the radius, and it's starting to curve the arc so that it fits in a circle. And they're the same, okay? If it's that big, it's 1 radian, okay? Okay, cool. Let's talk degrees. Degrees. Okay, cool. When we talk about degrees, we're familiar with those, right? We feel pretty good usually about what we've got going on when we deal with degrees. Let me just give myself a kind of a picture to work from here. All right, imagine my circles get worse and worse. Imagine that this is what we've got, and so all right, there's my terminal side, my initial side, my vertex, and around we go, right? And so we've got this trip around the circle that we can take. 4.2 is going to be unit circle stuff. We'll talk about that on Monday. But for now, what I really just want you to be able to understand is that 0 radians, and if you put the RAD, that's fine, but without it, okay? The assumed measurement system for angles is radians. So if I say 0, I mean 0 radians. If I say 5, I mean 5 radians, not necessarily 5 degrees, okay? But 0 radians, 0 degrees, all good. And I can take a full trip around. That's 2 pi radians. How many degrees? 360. Do you know why they kind of arbitrarily chose 360 degrees? Like, why the number 360? There's why. It is one of the most composite numbers less than 1,000. Okay, 360 is divisible by 1, 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, 18, 20, 24, 30. Oh my goodness. Forever and ever and ever and ever. There are so many ways to break that number up so nicely that it makes it really easy for us to divide this circle into however many pieces we want. Okay. Now, okay, so all the way around 2 pi or 360 degrees. So if we only go halfway, okay, like I said, half a revolution is pi, or it's 180 degrees, and those two measurements are the same, right? Pi radians is the same as 180 degrees. And I'm going to lean on that relationship. Like 1 foot is 12 inches, right? Same thing here. Pi radians, 180 degrees, same thing. Because what I want us to be able to do, obviously we need to know degrees, and okay, like 90's there and 45's there and 270's down there, whatever. But I want to be able to switch back and forth nicely. I want to be able, and this is the last thing we're going to do, is to convert either degrees to radians or radians to degrees. Switch back and forth between the two. Okay, so I could go from degrees to radians. I'll show you how to do that. And radians to degrees, and then we'll be done. Okay, so let's say they gave me something like 60 degrees. Okay, and I want to make the switch between degrees and radians. And if I don't know it off the top of my head, which I hope by the end of trig you do. You should really have these things kind of stuck up here. It makes it so much easier. I want to switch to radians, okay? And I want to do that in a pretty specific way to make this work. Number one, I got to get rid of these units, so that's no good. The other thing is I want to make sure that whatever answer I get isn't any bigger or any smaller. So what I'm going to do is I'm going to multiply by 1. Right? And I'm going to multiply 60 degrees by 1, but I'm going to pick a version of 1 that does what I want. Man, you've heard that enough from me this year, right? 60 degrees, all right, I'm going to put it over 1, times some fraction, same thing top and bottom. 5 over 5, 2 over 2, right? Radical 3 over radical 3, 2 plus 3i, 2 plus 3i, whatever, right? But I want to do it in a way that gets rid of these units. So if I have degrees on top, I need to divide, I got to put degrees on bottom so that those units will cancel out, okay? And if I want to end up in radians, I better make sure that my radian measure goes on top so that doesn't go away. I don't want it on the bottom of a fraction, right? And I can use this relationship that pi radians and 180 degrees mean the same thing, okay? And then I just simplify, right? Multiply straight across, but before I do that, I will simplify. 60 into 180 is 1/3. Okay, and the degree units are gone as well because you have degrees on top, degrees on the bottom. So 1/1, okay, so 1 times pi over 3. Pi over 3 radians. So exactly 60 degrees is exactly pi over 3 radians. If you're in a circle of radius 1, that arc length, when you go 60 degrees, is pi over 3. Okay, that this irrational number is so perfect. So all you have to do is multiply, that's a multiply, by pi radians over 180 degrees every time. That's it. Okay. You could do 2 pi over 360, but this is the simplest version of that. And radians to degrees is just the opposite, right? So if you have like 3 pi over 2, and so radians on top there, and I want to switch that to degrees, I know I'm a couple minutes over, but multiply by 1. Right? If I multiply by 1, life is good. What kind of 1 do I want? Well, I want a kind of 1 that's going to get rid of radians. So I had radians on top. I better put radians on the bottom. I want to end in degrees, so I better have degrees on top. What relationship could I choose? Well, I could choose 360 over 2 pi. I could choose a lot of different things that are all true, but the easiest one is 180 over pi. Okay? It avoids complex fractions and is nice and simple. Right? Because there go the radians, and hey, look, there go the pi's as well. Now remember, radians don't have to have a pi in them. This could have been just 3 over 2 radians. That's fine. You would have ended up with a pi in the denominator of some decimal spot, right? I told you, when we use 1 radian, 2 radians, like if we don't use pi, the degree measures are going to be irrational, pretty gross, okay? And now we just simplify, okay? 3 over 2 can't do anything there, but 2 and 180, I can. That's a 1. That's a 90, multiply straight across, 3 times 90. 1 times 1, right? There's just a 1 left down there. 1, right? 270 degrees. There you go. Okay, that's my beginning of trig. We're at 118. So if you gotta go, you gotta go. Test got graded, so if you want to stick around, if you have a couple minutes and you have questions, or if you want to just kind of chat back and forth on Canvas, we can do that. If you want to know what you got wrong and what you did wrong, I'm happy to go through that. That's fine by me. I take pictures of this stuff. I will put it on the announcement for today. This is being recorded, so I will post that as well. What you're going to see for tomorrow's work is you're going to do some degrees and radians converting, and you're going to do some of that, a little bit of the zero. Okay, S equals R theta, or theta equals S over R, or R O equals S over theta. Kind of like solving for some arc length, or solving for some radii, or solving for some theta measures in a circle. Okay, and it's going to be right out of the textbook. So it's going to be section 4.1. So if you need a copy of chapter 4 for some reason, if you don't know where your PDF is of the textbook, let me know. I'm happy to send it to you. But other than that, we are good to go. Check Canvas for that work for tomorrow. And have a great weekend. Thanks, everybody.
Thank you.
Thank you, Rosie. Bye, Rosie. Thank you.
Thank you.
Thank you. Adios, adios. See ya. Is that Tyler James in the building?
Thank you.
Hi.
How's it going?
Good, man. Does this bring back some fond memories?
It does. It does.
Makes you forget about calculus a little bit.
Yeah.
How's it going?
It's going.
Yeah.
Yep.
Yeah. I know. It sucks.
Yeah. I came home several weeks ago, and I got finals next week.
Okay.
But then I'm done until like January 25th.
I know the college schedule is amazing, isn't it?
Yeah, it's great.
Wyoming, right?
Yep.
Sweet. Nice. You liking it? I mean, obviously it's. So were you on campus, but like taking classes virtually, or?
Yeah. So I was on campus.
Okay.
I had one class that was